Thanks, Luca. I'm Ludwig. I work for SUSE for quite a long time. I'm in a team called the Future Technologies team, and we work on technology that is interesting for future releases. And my topic recently was integrating system deboot into openSUSE, so specifically openSUSE Tumbleweed. And when talking to people, I realized that I don't even have a slide that explains what Tumbleweed is. So if you're not into the openSUSE ecosystem, Tumbleweed is the rolling distribution we have in openSUSE. And the special thing about it is that it is actually tested, so there's an automated testing infrastructure that makes sure every release that goes out, that might be every day, is actually bootable and has some minimum quality standards. So that, and at the same time, it integrates new changes almost every day. So you get a systemd when there's a new release, like within a week or so in Tumbleweed, unless it triggers the quality assurance, and then it might take longer to fix issues. So anyway, let's go to the why do we want to have system deboot in openSUSE. So on the technical side, the reason or the main motivation is full disk encryption. Because with grub, the current way full disk encryption works is that grub has to unlock the LUKS volume. So all the decryption code, the password derivation functions and all that stuff has to be in grub in addition to the kernel. So it took quite a while actually in openSUSE to get the Argon 2 support for LUKS 2 implemented, because grub didn't do it. And even when grub does those crypto operations, they might be slow. And it's of course a lot of code to have that in the bootloader. And also grub, after opening the LUKS volume, also needs to access the Linux file system to get the kernel, which in our case is Btrfs with snapshots. So all of those features have to be implemented in the bootloader. Now with system deboot, everything is much simpler. It's just a UEFI bootloader that can only read files from the EFI partition and has nothing to do with the Linux files. So all the heavy lifting can be done by the Linux kernel, and the code already exists there. Also Linux user space in the initRD, which also can do a lot more than the bootloader. The advantage of going for system deboot is also that you don't really have to use system deboot in the end, but you could also just use the architecture that system deboot uses and use another bootloader. So we could still stay with grub, but just drop all the unnecessary code if you go for this architecture. So there's benefits of implementing a simple solution basically, and start with that one instead of going for the complicated one with grub. So let's see how system deboot is actually installed. So that should be pretty easy. It's in the systemd package in openSUSE, so it's just called boot control install. The upstream tooling would copy system deboot into the EFI partition, both in this boot directory that is for removable media basically, and in a systemd directory. It registers a boot variable, and there you have it. It's bootable. Alarm again. Sorry. So looks fine, right? But for general purpose distribution, the first hurdle is already secure boot. So if you want to have this on a real world laptop, you probably have secure boot enabled and don't want to disable it. So the first thing you have to do to get system deboot on screen is to somehow sign it. You would do that with a custom certificate, because Microsoft won't sign your own code. And if you do that, you need shim. Shim is signed by Microsoft, at least in openSUSE, and shim can load other EFI binaries. If they're not signed by a trusted certificate, there's ways to have shim import a certificate so it can actually load system deboot in the end. With a trick, because shim insists in calling the thing it loads grub.efi, so we need to rename system deboot to grub basically, and then shim would load it, provided it's signed with a trusted certificate. That however means that if we follow the structure of that shim wants, then we can't use boot control install, because boot control install creates a different structure on the ESP. So systemd boot control actually needs to be told about shim, and needs to know how to do that when shim is in use. So the layout looks like this. In the generic boot folder, there's shim, and if on removable media, it would boot, and it would look into subdirectories, find this boot.csv, and that boot CSV specifies that there's systemd boot in there, and then would register the EFI variable. Mock Manager is this tool that actually manages additional certificates for shim. So with this, we have a working systemd boot, but it wouldn't do much at that point. We also need to create entries. How do we do that? Entries boot kernels and initrds. Fortunately, in openSUSE, the kernels already have PostScriptlets where we can hook into. And another advantage is that the scriptlets are not actually in the RPMs, but the RPMs themselves just call external scripts. So it's pretty easy to simply replace those scripts with scripts that install systemd boot entries instead of grub configs. So I just had to convince the package maintainer to create a separate subpackage for the scriptlets and then introduce another subpackage with systemd scriptlets. So in there we can just call kernel install and then get entries on RPM installation of a kernel, and it removes entries on kernel removal. So quickest talk ever, right? We're already done. Everything already implemented, nothing to do. Here comes the catch. SUSE uses Btrfs by default, and we use snapshots. So there isn't just one kernel in one root file system, but there's potentially hundreds. And on top of that, it's not just one way to use snapshots, it's actually two. So there's the classic mode. If you go ahead and download Tumbleweed today, you get a read-write root file system, and it would do snapshotting on that, so install kernels in your live system, like you know it from other distributions. And the other mode is a transactional mode. In that mode, that is used by MicroOS by default, the root file system is read-only, and when you install packages, it would actually install them in a future root file system that is only active after reboot. So I'll explain that in a slide. First, the read-only system, because the diagram is easier. So we start off on the top left with the current snapshot, would be a read-only root file system, in this case snapshot 42. When you want to install packages, the system would create a read-write snapshot, do basically a change root, and install all the package changes into that snapshot. When done, we would set it read-only again, and at that point we would need to register it with systemd boot to make it bootable. So copy all files required for booting into the ESP, and also mark this new snapshot as bootable, as default. That looks quite easy, but already we see that the hooks that are in the scriptlets actually don't do anything in this model, because you only set the snapshot bootable after it's done. I mean, if there's some failure in the middle of preparing this new root file system, it would abort and shouldn't have any effect on the boot files. So this easy way with the scriptlets doesn't work here. We have to hook into the snapshotting system in addition. Let's take a look at the classic read-write. That looks a bit more complicated. So we again start on the top left corner with the current snapshot 42. This time it's read-write. In this model, when we want to install packages, the system would first clone the current root file system into a read-only snapshot. And in order to be able to select that in the boot menu, we would have to edit boot files at that stage. Again, no RPM scriptlets involved. This is again the snapshotting system. Then the package manager can modify the root file system. At that point, kernels get installed probably, and then the scriptlets run and would add the boot files, like calling kernel install. When a kernel gets removed in that stage, it would remove its files, right? Well, that would be a bad idea, because we create a snapshot that should still be bootable, so it can't just remove the kernel that was used in a different snapshot. Anyway, when done, it would clone again the final result and create a post snapshot, again read-only, just in case. And that one also needs to be made bootable. So what does adding boot files actually mean? First of all, it means copying kernel and initd to the ESP. But we can't just use some unique identifier per snapshot, because the space on the ESP is limited. So we always need to keep that in mind. When working with the ESP, we can't just put arbitrary amounts of data in there. That means we somehow have to deduplicate stuff manually because it's fat. One thing to keep in mind when looking at the upstream proposed naming scheme for those files is that a kernel with the same version, 5? 10 minutes. 10 minutes, okay. Kernels with the same version may not actually be identical. So openSUSE rebuilds files on server side when they change. So when there's a new compiler checked in, for example, you could get a kernel with the same version, but compiled with different compilers. So you can't just put this kernel version 1, 2, 3 somewhere and say this is kernel 1, 2, 3, but there needs to be some way to have them when they are not identical. Same for initrds because they contain user space changes. So for a given kernel version, there might be multiple initrds actually. And since we want to deduplicate stuff and reuse them as much as possible, we can't have the root subvolume encoded in the initd. Like what Raycard does nowadays is embeds the root volume in the initd. That doesn't work. So we need to pass that in the entry actually, which also needs to be generated. So a few words about initd. Need to speed up a bit. Generating an initd is expensive. So in this read-write example I made, where it creates the snapshot before installing packages, we for sure don't want to create an initd because then all package operations or creating snapshots would become slow. So we need to somehow reuse initrds as much as possible and not regenerate them without reason. So the way how to do the deduplication is adding checksums, at least that's what I came up with. So an example file system tree on the ESP would look like this. Upstream bootloader specification naming scheme, the machine ID, then the kernel version. And instead of just calling the files Linux and initrd in there, I just appended a checksum of the file. So that way there can be multiple initrds and multiple kernels. And for the entries, I appended the snapshot number, because again, for the same kernel, it could be used in multiple snapshots. Would be kind of cool to use an add sign there, but it's fat, so you're limited with the characters. So there's actually a dash only. Let's take a look into one of those entries. This is how an entry looks like right now. Title is standard. Then I had to put the snapshot version in the version, because otherwise you have lots of entries that refer to the same kernel version. It's a bit weird because the snapshot number is in front. That's for the sorting. Otherwise it would sort by kernel version, and then the outcome is a bit weird. Then we see here in the options, pass the root volume and the subvolume, and then refer to kernel initrd. So consequences of doing that. Raycard can't just put the initrd where it thinks it could put it because it has to append the checksum. And even if we teach Raycard to append checksums, that would mean there's no entry referring to the initrd. That means Raycard is out of the equation basically. It needs to be patched somehow to not generate initrds if you call it. Another consequence, kernel install can't just remove files because it might be used in other snapshots. And in fact, it also does other things like calling depmod and removing depmod. That is devastating on a read-write system because it removes generated files in the live root file system and then wouldn't boot on next boot anymore. So instead of calling kernel install remove, I introduced this boot control unlink command where you can tell it to unlink an entry and then would do some reference counting on all the referenced files. Yeah, so let's take a look at the menu. This is how systemd boot would look like with lots of snapshots. As you can see, it's not pretty, especially in a read-write system. The current snapshot has a lower number than all the snapshots it created, so it's somewhere in the middle. That is for sure not user-friendly. But there's already a patch submitted upstream to add some kind of submenu support. Not sure how the final solution looks like, but yeah, that is something that needs to be solved. Okay, next one is talking about sdbootutil. So as kernel install has some limitations, and I tried several iterations upstream to get it do what I want, but in the end it was complicated and none of that was pretty. So I decided to speed up the thing and write my own shell scripting until I know what I want exactly. So that's what sdbootutil is doing. You can manage the kernels in the ESP, show which ones are in there, which ones need to be copied in there. It can make snapshots bootable because in the end you don't want to say I want this kernel bootable, but you say I want this snapshot bootable. So what it implements is basically boot control install, to install shim along with systemd boot. It does what kernel install add and remove does, just with snapshots. And it does what boot control set default does, just with specifying a snapshot. It shouldn't do any of that. So the goal really is to drop this tool at some point and integrate all of that upstream once we know what we need exactly. So this is how it looks like. It's a dialog-based shell script. Someone told me I'm the only man on this planet who still writes dialog-based shell scripts, but it's actually quite nice. So this is a feature where you can see which kernels are in the ESP related to the current snapshot. So the kernel might be installed, then it's okay. It might be stale because somehow someone forgot to remove it. Or it might be installed as package, but actually missing in the ESP. And this tool displays all of that. I think such a thing is needed, actually. Just this plain kernel install, where you don't know what the state is not sufficient for usability. So you really want some overview. So what's the status of all this in Tumbleweed? Systemd boot is usable. The tooling is in Tumbleweed. There's a wiki page where you can follow like 3 steps to replace grub with systemd boot. It integrates with the snapshotting features on both microS and the traditional Tumbleweed. YAS support is meanwhile on the way. A colleague implemented that, so soon you will be able to select systemd boot during installation already. And there's also a microS appliance planned that has systemd boot out of the box. And also Richard told me that he wants to have a systemd boot by default on Eon. So there's a talk later from Richard about Eon. Yeah. So the conclusions. We need to talk about kernel install. What we need in there. Is it suitable? Is it needed? And as I said, we still need some tool for consistency checking, not just for adding and removing files. The menu needs some love and thinking how it looks best for users to do the rollback. Also, we need to think which information to present there. Right now it's pretty basic, but Tobias also thought about that, because in grub we have like the time when the snapshot was created and other meta information that might be useful. Yeah, from openSUSE side, we may want to switch to pre-built initrds. Not sure we would switch to UKIs directly, but at least having server-side as RPM installed initrds would be easier for this tool. Unsolved issues are updates of systemd boot itself. So I really think it should do some AB style updating of itself. That's a feature we don't have with grub right now in openSUSE, but since we are switching to something better, we could also do it better. And what's also missing is this boot assessment. So when a snapshot is not booting for whatever reason, it should actually automatically roll back in case of microS. That is implemented right now with grub in microS with health checker. But we need to integrate that still with systemd boot and this blessed boot mechanism. So still work to do. And last but not least, a few links. There's a microS image. I built that in a separate project. It's not official, but that one has systemd boot enabled by default if you want to try it. It's for KVM. Then the mentioned wiki page is just a few steps to convert a regular Tumbleweed to systemd boot. I'm tracking the open issues, the to-do items in Redmine on openSUSE side. And last is the link to this tool that I wrote that hopefully needs to go at some point. Yeah, that's already what I wanted to say, so open for questions.
Well, I have the first question. I thought we did have boot counting and boot assessment already. Don't we have targets for that?
Yes, you do. It's just not integrated in openSUSE.
Oh, so it's openSUSE needs to integrate it, not upstream. Perfect, yeah. Thank you. I think it was Anna raised hand here. Yeah, there we go.
So currently it seems you have one initrd, but if you split up the initrd into two, one without the kernel modules and one with just the kernel modules, can't you reuse the same initrd without kernel modules for even more kernels to save even more space?
That's what I have in mind, yeah. So I think we should build a host-independent generic initID as RPM, and then decide on the client what to put in addition. And I think we don't even need an initID that contains kernel modules. I think we could even put the kernel modules right next to the initID, because they are signed already. So I think we don't need to wrap them in a CPO or something. But I didn't think this through. But in general, the idea would be to have a generic small initID and then put the specific files next to it.
So many of the challenges you seem to be confronting on the openSUSE project with this are challenges that I think a lot of distros have, especially around integrating atomic systems and changes. I think you referred to it as transactional in the openSUSE case with areas like the bootloader. Do you know if any coordination is actually happening among distros on this, besides leveraging some of the same tools from systemd? Because I feel like multiple distros, I'm mostly familiar with Silverblue in this space, are really challenged in actually making and especially completing this journey. And many of the challenges you're showing up here are the same ones that I see, say, Fedora encountering. And I'm wondering if some of the same solutions or tooling is applicable, or if you're aware of any kind of inter-distro coordination on these challenges.
Yeah, that's why I'm giving this talk, basically.
Also, we have the UAPI group that we founded last year. Do you know uapigroup.org? There's a GitHub organization website, and there's a cabal behind it. But this is exactly what we do, right? Common solution. But yes, we are a lot of systemd developers, so lots of systemd tools. But it's not limited to that. So if you're interested, you can join that effort. We have open discussions on the GitHub org on this stuff. So.
But I mean, openSUSE is special in that regard because we use the Btrfs snapshotting. So I think most actually use this AB or ABC model with a real read-only operating system image, and we have those snapshotting features. But I guess others will catch up if that turns out to be really good.
Any other question? Yes.
So more of a comment. So we add a sort key, so maybe you don't need to play with the version field.
Yeah. Yes. I mean, we tried several combinations, and I think there's no real good one. But it's trial and error, I think.
Yeah. So we don't have the boot counting for SD-boot itself, right? We should implement that though, if it's missing. We have it for the UKIs, but not for SD-boot itself.
Well, we cannot do boot counting, but we should install 2 menu entries so that the user can fall back to the firmware menu if it fails to boot.
I mean, regarding the A and B thing of SD-boot itself, it certainly is something we want, and we can do this with registering 2 versions in boot EFI variables. The reason why I didn't do this is mostly because there's also still shim, you know, and shim also needs to do that, at least on systems where shim is in the mix. And then shim, however, so far always insisted on invoking one fixed payload, which is called grub64 EFI, right? So there is some work to be done. But Luca, like, I mean, I opened a request on the shim issue tracker that they please add this ability that they can actually look in a directory, right? Like, so that they enumerate multiple EFI binaries, try the first one by alphabetical order. If that works, great. If then try the second one and things like this. But anyway, so the problem is bigger, right? Like, you need the AB on the boot level, you need it on the shim level, and yeah, so that's why nobody ever implemented this. There's an issue open on GitHub systemd though to deal with these things, and I think there's nothing stopping us doing this. So it is makes some things more complicated, because the old TPM specs, they basically say that whenever you try invoking an EFI binary and it doesn't work, there's a measurement thing generated, right? And that is shit, right? Like, because that basically means it's extremely hard to predict. Like, ultimately, you probably would have to reboot. every time where the entry doesn't work, and you realize that the previous entry didn't work, if you recognize in the event log that this is what happened, right? So that there are complexities. Maybe we can ignore this because the newer versions of the spec say that if the validation of the selected boot item doesn't check out, no event should be generated, right? So that this doesn't happen. But yeah, what I'm basically saying is that there might be complexities with making the AB stuff reliable on old stuff. Probably on new stuff it should just work. Yeah.
I mean, there's for sure more dragons. So far I turned a blind eye on this TPM stuff with this. First I want to get the basics working and then think about the real hard problems.
Yeah, I think we're out of time now, so thank you, Ludwig.
Thanks.